Alright, welcome. In this video we're going to take a look at the data structure of a binary search tree. Binary search tree is a very common data structure used in computer science. There's a number of different variants of it, and it's been generalized in a couple different ways. And we're going to start today just looking at the basic, most general version. We sometimes call it the naive binary search tree. No special bells or whistles, just the normal binary search tree. So let's dive right in. So the characterizing invariant for a binary search tree is fairly straightforward and easy to understand, and it's can be depicted here quite easily with this simple picture. If we have a node here with value x, then all of the nodes in the left subtree have to have value less than x, and all of the nodes in the right subtree have to have value greater than x. And this basically enforces an order, a sorted order, if you will, upon the members of the tree. And it, among other things, allows us to easily search for elements in our tree. So we can take a look at this example binary search tree here. We can maybe verify for some of the elements here. If we look at the 14 here, we can, yes, quickly verify that all the elements in the left subtree are indeed less than it, and all of the ones in the right subtree are indeed greater than it. And we could, recursively apply that to other nodes too. We can see for the 10 node, all the ones to the left are less, all the ones to the right are greater. Of course, I've taken effort to make sure that this was a binary search tree that didn't violate any of the invariants by moving some of our nodes around, moving the 13 over here. That might satisfy the invariant for that local node 16. A 13 is less than it, but it's not less than, or rather it is less than 14, and it should be on the left hand side of 14, because it would be in the right hand subtree of 14 in that case. That would be an incorrect location for the 13, and that's the type of error you might encounter if you're working with binary search trees, usually by hand. By code, if you've actually programmed one, hopefully you've got your code correct, and you'll never end up with an error where you've added a node into the wrong location. Now, there is the possibility through some of the operations, which we will see later on in this video, or probably not in this video, but in a future video, where maybe doing an operation on a binary search tree might accidentally put a node in the wrong location. Say 13 was over here. And we might have to swap it over, and that would be a case where we would move it to where it actually belongs. And so we'll take a look at some of those operations when they come up. But for the most part, if you actually perform your binary search tree operations properly, you should be adding a node where it belongs. We'll see that in a second. Okay, so we verified this is a binary search tree. It satisfies the invariant. The primary purpose of a binary search tree is for searching efficiently, and it's called the binary search tree, and the name carries a lot of different meanings. Actually, it's a binary tree, so we might think of this as a binary, the binary in binary search tree meaning binary tree, but the binary search in binary search tree also tells us how we might do a search. The search in a binary search tree mimics a binary search. So say, for instance, here we might want to search for a node. I've got an example here. Say I want to search for 13. If I do so, I'm going to start at the root node. We'll always start our searches at the root node, and we'll compare the node to our current node. So if it is less than 14, we will go to the left. If it is greater, we would go to the right. So 13 is less, so we'll move to the left here. And then we will again compare to 10. It is greater, we will move to the right, and indeed we find the node that we were looking for. So we can see here, that's all I've got stated here, is that following our invariant, if the target we're looking for is less than the current node, we go left, otherwise we go right, and we keep doing that until we find our target. In our example there, we found our element 13 after visiting 1, 2, 3 nodes. Or in general, the node that we're looking for, the target node, I'm going to call this, it's going to be at some depth in our tree, and we're going to visit the number of nodes along the path down to that depth. So we're going to follow exactly one path from the root node to the node we're searching. So here I'm just leaving that as D, depending on how, we don't know at the moment how deep that might be for the particular node. If we're lucky, if it's the root node, then that's a constant depth. If it's a leaf node, well, it depends on how many nodes there might be in our tree. But for the moment, I'm going to leave that just as order D, where D is the depth of the node. Let's do another quick example here. What happens if the node is not in the tree? Well, again, we'll start out at 14. If 15 now is greater, so we will recurse to the right here, which is node 16. Again, it is less. And here we might look to the left. In this case, in an actual programmatic concern, we'd probably have a null pointer here. We'd see a null node, and we'd know there's nothing there. We'd probably stop our recursion here. And usually the idea is if you find an empty location, a null position in your tree when you're doing your search, then that means the element that you were looking for was not in the tree. So this is a negative case, or a negative occurrence for our output. We should say, okay, the element has not been found. Again, we are guaranteed that's the case as long as our invariant is true. We trust that the invariant is true because this is the only position in the tree where 15 would belong. Okay, and verify that for yourself. Because it is greater than 14 and less than 16, this is the only location where it would belong. All right, that also sort of hints to us what we're going to do if we want to add a new element into our tree. But before we get there, I want to point out a second important benefit for having our nodes in a binary search tree, or our values in a binary search tree, which is if we carry out an in-order traversal. Now remember, in an earlier video we talked about traversing our tree, and the traversal of a tree here carries out a depth-first search where we sort of go through the tree in this fixed order here. And as we do, we can perform operations on the nodes depending on what we want to do. And in this case, I'm thinking maybe let's output them. So in this case, if we did an in-order traversal, the first one that we would output here would be the 3. In order, remember, we output them during this path when we encounter them at the bottom of the node. So the next one would be 4, then 7, then 10, 13, 14, 16, 17, 19, and 21. And if we're careful here, we see that that gives us all of the nodes, the values that are stored in our tree in this case, in ascending order. That's because we have the invariant set up in the way we do. And maybe we want them, maybe we want our nodes in ascending order. Often sorting, we talked about sorting in a number of videos. Well, this gives us the idea that if all of our nodes are already stored in the binary search tree, then we can extract them, if we want, in order, in ascending order, so sorted, if you will. You can think of that as the sort operation. We can extract them with one traversal, and one traversal takes us order and operations. Now that's pretty good if what we're doing, say we want to sort some elements, if they're already in a binary search tree, then sorting them, they're basically already sorted and we just have to read them out. Okay. The problem is this does not take into account how many operations it takes to put them into the tree. And so if we're starting with a bunch of elements that are just in a list, they're being entered by a user, something like this, then we have to take into account the cost of putting them in the tree first, and then we can read them out pretty cheaply. And the cost of putting them in the tree, spoilers, is more expensive than order n. So I'll leave that to you for the moment as an exercise, and maybe I'll comment on that later. So if you want to think about that while we're going. Okay, so I mentioned that adding to a tree is pretty straightforward once we understand how searching works. So when we want to add to a tree, there's actually only going to be one location in a tree where we can legally add if we don't want to violate our invariant. Now, it's probably worth mentioning at this point, some of you may have already had a question, which is, what about duplicates? What do we do in the case of duplicates? Well, I'm going to do the easy answer right now, which is I'm going to assume there are no duplicates for the moment. And that's going to be usually the simplifying assumption we're going to make whenever that question arises. What do we do with duplicates? The first answer is we're going to pretend they're not there. And the reason we're going to pretend they're not there is because the second answer, the longer answer, is usually, well, there's usually some logical way we can handle duplicates. Now, in the case of binary search tree, it's probably what we're going to do is we're going to store duplicate entries all in the same node. If we have 16s, well, I'll just put them in the 16 node in a linked list or something like that. So for the moment, we only have to worry about nodes that are have distinct values when we're thinking about operations on our tree. Okay, I think that's important because that was important in our search. Okay, what happens if there is more than one element? Well, usually you only want to find one. Okay, but now it's going to be important in our add. So what that means in our add is if we find a node, if we're trying to add a 16, for instance, and it's already in our tree, it doesn't affect the shape of our tree at all. We just find that node and we just insert it. Now I'm going to ignore those cases because they're just sort of a special case, and instead I'm going to think about only adding new nodes where we have a new value. Okay, so if we're going to do that add, we're going to start out by doing a search for the element in the tree, and then, as I say here, we're presumably going to find an empty location, and when we do, we just add the element there. And it's pretty straightforward again to see that this add is the dominant part is the search, finding the position to put it, and then well, wherever we add it, the depth of that node is going to dominate this operation. So let's do a quick example with our node 15. So we did a search for 15 before, and that brought us here. But with an add, we will add that new node in when we find that empty location. Okay, so adding is actually fairly straightforward. You just add in the location where it belongs, and actually removing is pretty straightforward too, except it has one special case that we're going to want to maybe look at in a little more detail. So I'm going to maybe mention here, say we want to remove a node V. Well, again, to start out, both the add and the remove begin with the search. The search is the key operation. If we want to remove a node, first thing you do is find it. Okay, so we start by finding it, and then we actually have three possible cases. And the three cases that arise based on how many children our node has. So we have a couple possibilities. If our node has 0 children, then it's what we call a leaf. If it has 0 children, well, deleting a leaf is actually the easiest thing that we can do. Deleting leaves in trees, right? That's like pruning your tree. Those are the parts of the tree that are easy to cut off, right? Okay. So that's the easy one. If we find a leaf, it's safe to remove it. We'll just remove it. It doesn't violate our invariant in doing so. There's no chance that it will, so we're good. Okay. Next possibility is what happens if we have one node. Well, actually, let's just look at the example first. Let's look at removing, say, 13. So removing 13. In this case, it's a leaf. Boom, we're done. All right. Okay. So then the next question might be, well, what about removing 10? 10 here is a node that has only one child. Okay. Now, the idea when we only have one child is what we're going to do is we're going to remove that child, but then we have to do so, or we're going to remove that node rather, and we have to do something with the child. Now, because it only has one child, it's going to belong, that one child will belong no problem right where the parent was. So we're going to promote the 4 up and make it the new left child of 14, as we'll see in this case. And it's still true because now at the moment, 4 is a left child of 10, so that means it's less than 10. So we know it's less than 14 as well because 10 is a left child of 14. So certainly we know that it's not going to violate our invariant. But even if it was on the other side, remember, anything in the left subchild of 14 will be less than 14. So no matter what child 10 has here, the left or the right child, we know that will be less than 14, and it will be an okay new left child for 14. So after removing 10, we just promote our node 4 up to that location. And its children, the whole subtree, come up with it. And notice, just check for yourself, the invariant is not violated in that case. So that leaves us in our last case. What happens if we try and delete a node with 2 children? Now, here for my example, I said why not delete the root node? Now again, we saw this when we were looking at heaps, but deleting the root is the worst thing you can do for a tree, right? If deleting leaves are the easy thing to do, then deleting the root is how you kill it. So this is probably the hardest thing, which means we need to be clever and careful. Now in heaps, the idea was why not swap it, promote it, swap it with something we can remove, right? And actually that's the exact same idea we're going to apply here. It's just because the invariant on heaps and the invariant on binary search trees are different, the node that we can swap it with, the node that we're allowed to, is different. Okay, so let's think about that. Now, the idea here is we want to delete the 14, but we can't because it is, well, it's the root in this case, but it has 2 children. If it had 0 children or 1 children, then we know we're good to go. Okay, so in this case, what do we have to do instead? It looks like what we need to do is we want to promote a node, but what node would fit well in this position? We can't just pick any node. For instance, the 3 is the minimum node, and it would violate our invariant. It would mess things up. We'd probably have to swap a few other things around. We don't want to do that. But you'll notice, if you notice carefully, and we could go through all of the nodes and check all of them, there's 2 of them that would not violate the invariant. One is the 7, and one is the 15. And the reason is if we actually again did the in-order traversal, the 7 is the node that comes right before 14 in that traversal, and the 15 would be the one that comes right after. So these are actually the nearby neighbors of 14 in the sorted order of the whole list. But the way we could find them is the 7 is the largest node in the left subtree, the greatest node in the left subtree, or the 15 is the smallest node, the least node in the right subtree. Okay, and here actually we have a question. Well, how do you find the smallest node in a binary search tree? Now think about that for a second. How do you find the smallest node in a binary search tree? Well, if you're at a node that has some children, if it has a left child, that left child must be smaller. So you go to the left. You keep going to the left until you don't have a left child. When you get to the left and you don't have a left child, that must be the smallest node in your tree. Does that work in my right subtree here? Start here, go left as far as I can. Well, that's here. That's my smallest node. And going right as far as you can gets you the maximum node. That's true. Going right as far as you can gets you the maximum node. So we can find that quite easily by, again, just traversing. Remember, these are usually implemented as linked structures. You usually just say, okay, go right, go right, go right, go right, until right is null. Okay, so with our 14, we need to promote one. I'm going to swap it with the 15. And then I'm going to delete the 14. And when we're done, again, the invariant is satisfied. Okay, and we have a nice binary search tree here. Okay, I think I somewhat skipped over this as we were going through, but the running time or the number of nodes visited for the remove operation is again order of D, where D is the depth of the node that is removed. Now that's a fairly straightforward, except in case 3 here where we need to be careful. Say in that case I actually wanted to remove the root, but because I swapped it with a node that was lower down, it was the depth of the node lower down, the one we actually remove. Okay, that is the order of the depth that we need to consider in the number of operations. I will also mention in all 3 of these cases, I've got maybe a summary here now. I've considered the number of nodes we visited on the way down as my tool of analysis. And that's assuming that every time we visit a node, we only do a constant number of operations. And usually that's going to be the case, even if we were swapping nodes or something like that. And so we're really concerned with how many nodes we access in any operation. And so for all 3 of these operations here, search, add, and remove, these are the sort of the most important operations for any data structure. When we were considering lists early in some of our earlier videos. Add and remove were the dominant mechanisms we looked at. But then we also thought about searching, and of course, sequential search and binary search were our two common search methods. Now that we've shifted away from list types, we can again think about these operations. For heaps, heaps are very specialized. And in fact, for heaps, search is not an operation that is implemented. And this is because heaps are an implementation of a priority queue data structure. Remember, our abstract data type is the priority queue, meaning that heaps typically operate as a queue-like structure. And since they operate as a queue-like structure, queues are not the kinds of structures we typically search. And so we usually don't implement a search operation on those type of structures. Instead, what we want to be able to do is add elements and remove elements. The only thing the heap allowed us to do was add priority to our elements. Now, moving into a binary search tree and foreshadowing in some of the future videos, I want to look at more data structures where the goal of the data structure, the primary purpose of the data structure, is to store data, like in a database, where that data is probably going to sit there for a while. It's not like a queue. The thing about a queue that makes it special, and also a stack in most of the cases when we use it, is we fill it up, but then we empty it out as well. We fill it and drain it. The whole purpose of a queue is it's some things that are waiting for what to get out of the queue. We want to clear them out. But other data structures, binary search trees, and normally lists in a normal array list or linked list that we might use in any other programming, not a queue, not a stack, usually we are keeping that data around for something. We might be processing it, we might run a couple different algorithms on it, it might just be sitting there for our user to do something to it. And those type of data structures, we now want to build the data structure in such a way that it makes accessing that data as simple or as quick as possible. And lists are simple and quick as long as the amount of data we have in there is fairly small. The n part that we're looking at is fairly small. The purpose or the motivation of moving towards binary search trees and other data structures now is that we want to get even better access. So access in what way? Well, searching, finding an element. If I don't know where it is, how quickly can I find it? And then the other two main important elements are adding new data in and deleting something if there's something in there. Now, usually adding and deleting are tied to search, and we've seen that that's true here in the binary search tree. The dominant operations of both our add and our remove operation was just the search. Finding the location to place it or finding the element to remove. Those were the dominant cost of those two important operations, add and remove. Now, importantly also, I have sort of been agnostic about what D is. What is the depth of our binary search tree? Well, the depth of a binary heap, we remember a binary heap has this complete left-loaded binary tree property, which ensures that the depth of the heap is very small. In particular, this represents the best case for our binary search tree. We might get a depth of about log n. Remember, this means log base 2. So here we have log base 2 of n as the best case for our binary search tree. And I'm going to show an example of that in a second. And then the unfortunate thing about the binary search trees, though, is there is no guarantee that we're going to have that good depth. The binary heaps enforced it. It forced us to make sure the structure of our heap was always this complete left-loaded binary tree. That ensures us efficient operations. But with the binary search tree, nothing in our invariant told us that we had to keep things, nice and balanced or keep our tree sort of complete. So because of that, we can get some bizarre binary search trees. I sometimes call them degenerate binary search trees because they don't actually fit the spirit of the binary search tree. Even though they match the definition, they maybe don't match the spirit very well. Okay, so I do want to continue with a few more examples working with our binary search tree for just a second. Just to sort of finish off here, I want to hint at coming up video, maybe not the next one, we're going to start looking at some binary search trees that actually balance themselves. So they'll detect when they get imbalanced, and then they will balance themselves. So that's coming up. But for now, let's just do a closer look at our binary search trees and the kinds of shape we might encounter with the binary search tree. Now, I mentioned that there's the possibility that we get this degenerate tree. Now, to show you an example, I'm going to let's just consider some simple binary search trees built out of maybe, I'm going to say 7 numbers. Now, I picked 7 for a special reason. Well, it's a 2 to the n minus 1, in particular 2 to the 3 minus 1, which means it has a nice property. And if you've been paying attention to the past videos, you might be able to remember what that property is and why I picked 7. All right, think about that for a second, but for the moment, I'm going to say let's practice adding to a binary search tree, and let's just see what happens when we add these numbers in this order. So remember, when we add, there's always only one location to add in, and when we start with an empty tree, that location is the root. So we're going to add 1 in as the root of our binary search tree. Okay, 1. Now we're going to go to 2. And when we add 2, remember, we search for the location where it belongs. Well, 2 is greater than 1, so 2 belongs here. Okay, moving to 3 then. 3 is greater than 1, so we go to the right. 3 is greater than 2, so we go to the right as well. And we can see here, continuing, well, 4 is greater than 3, so 4 must keep going all the way to the right. And again, 5 is greater than all our numbers, so we go all the way to the right. So we can kind of see that indeed, if we add our elements into the binary search tree in this order, we get one of my examples, what I call my degenerate tree, or a stick or a branch or whatever you want here. It's not really a tree, and as a result, the depth of this tree is order n, where n is the number of nodes. All right, that doesn't sound very good. Here maybe our n was 7. What's the best we could do here? Well, probably we don't want 1 as my root. I just draw my 1, but probably would be good if I had 4 as my root, right? Okay, because then I would only have 3 nodes on one side and 3 nodes on the other. And maybe we can already see that if I split those up properly, like that and like that, I can get a binary search tree now that has depth 3. And the cool thing about this one, this depth, is it's actually about log of n. Technically, it's log of n plus 1. Okay, 7 plus 1 is 8, which gives us 3. Okay, or the floor plus 1. There's a couple different ways you could calculate it, but remember, when we're talking about big O, the asymptotics, those plus 1s, those minus 1s, the floors, the ceilings, maybe even a leading constant, a 2 or something, those things don't matter. We're brushing them under the carpet. What does matter here is the difference between the n and the log n. And remember, that's the difference or the gap that we can get ourselves into when we're dealing with binary search trees, is we're no longer guaranteed to have this nice form. This is like a heap form, that complete binary tree form. That guarantees us the log n runtime, but we could end up with something degenerate like this if we add our nodes in the wrong order. And this isn't the only order we could get. Here's sort of another weird case. Let's see if I can do this right. So we could do 1, and then 3, and then 2, and then, oh, I guess that one doesn't work. I need 2.5 here. But the idea is you could make another one that kind of wibble wobbles its way down like this. I think I probably needed to start with a 7 here if I wanted to do it properly. But you could get something that kind of wibble wobbles like that on the way down, and it's still degenerate. It still has order n. So this isn't the only one that gets you a bad case. Of course, you could have one going down the left side too, or one that wibbles wobbles down the left side, or a whole bunch of different ways you could wibble wobble. There's lots of ways you can get an order n. There's also lots of ways you could get into a nice tight form, but the way we designed this one here to get this perfect form, this is the only way. There's no way we could have done this without putting our 4 here and our 2 and our 6 here exactly. But there might have been ways that could get us just one depth deeper and have a little bit of freedom there. And that's really going to be the topic of a future video when we start thinking about rebalancing our binary search trees. Okay, I think in the next video what I want to do is just practice working with binary search trees again, doing adds, removes, and so on. And then after we get comfortable with that, we'll move into our first self-balancing binary search tree. We're actually going to look at 2 different kinds, AVL trees and red-black trees. All right, thanks for watching, and we'll see you in the next video.